Hi CTM students, welcome to the Chapter 10 practice test. It can be found on page 590 in your books. And so here's the same thing, that's what you see in the book. It's just going to go through each one of these problems one by one with you. You just watch what you need to watch to help you. If you want to skip around, you're totally welcome to do that. If you want to go through the whole thing and just to see that you got the explanations and everything down pat before the tests, make sure you basically use it how you feel like you need to use it. Well, let's get started on number 1 here. Okay, so what is a mathematical system? I've got my 10, 1, 2, and 3 completed notes up here. So going back to some of these things, you can always go back to your notes and let that help you here in your preparation for the test. So just going to rewrite what I've written here. So a mathematical system is something that consists of a set of elements and at least one binary operation. So we're just going to rewrite that basically. And to save us a little bit of time here in this video, let's see if I can just do this. I'm just going to copy and paste that. Right, so the book more simply states that it is a set of elements and a binary operation, so we've said at least one binary operation, but either one will work there. So let's move on to number 2. Let's requirements for a mathematical system to be a commutative group. So we had our CIIAC, that is what we're referring to in this case here. So going back again, oops, a little too far there we go, from 10.1. So we had closed, identity element, inverse, associative property, and commutative property. All those things needed to hold, and so I will just write basically those things. So it has to have closure. The following, I think this is probably the best way to write it, the following must hold. You've got to have those 5 things. So it's got to have closure, it's got to have an identity element, I could say must hold or be present, / be present. There has to be an inverse for each element, and the associative property must hold, so associative property, and the commutative property must hold. If it's just a plain old group and not a commutative group, then you just have to have the first 4, remember. So commutative property, that must hold as well. Alright, so let's move on to number 3. 3 asks, is a set of whole numbers a commutative group under the operation of addition? And explain your answer completely. So the way we worked these problems before, remember, is we just checked our steps. We go through the 5 steps, 1, 2, 3, 4, and 5, and just, I'm going to refer back to this one a fair amount, I think, just as a reminder, basically checking the CII. We sort of jokingly, but not completely, just kind of our mnemonic device to help us remember the central insanely intelligent agency, and then this extra C at the end. That kind of helped me remember how these go in order. So we're going to check these 5 things. Does the set of whole numbers first have closure under the property of addition? So whole numbers, you've got to remember what those are to be able to answer this question. Whole numbers, that's the set of numbers from, and if you forgot, you can go back to 10.12. I do want to just remind you of this thing that we had here. So whole numbers, the natural numbers include 1, 2, 3, and so on, all the positive numbers, integers basically. The whole numbers also include 0. So we have the whole numbers being 0, 1, 2, 3, 4, and so on. It continues on and on forever and ever. So checking the steps. Step 1, this is problem 3, but it's step 1 here. Does it have closure? So I'm going to check for that first C. Does it have closure? If you add any of these 2 numbers, are you always going to get another number in this set? And that's going to hold. So I would say closure is good, or closure checks. Now, does it have an identity element? Is there something we can add, since the the set is under the property, or under the operation of addition. There's something you can add to each number that gets you that same number that you started with. 0 is that number, so the identity element is 0. So let's say that checks out too. That's my first I. Now does every element have an inverse element? In other words, can you add something to each number in this set to get you this identity element, to get you 0? So here is, if you say no, you're exactly right. Here's a counterexample. You can pick any number but 0, and it's not going to have an identity. So a counterexample, 2, I would say maybe more something like this. 2 plus negative 2 equals 0, but is negative 2 an element of the set of whole numbers? No. So negative 2 is not a whole number. And so does this hold? We don't have to go any farther at that point. We would say no, because not every element has an inverse that is a whole number. If you said the set of integers, then you'd be fine. But if you're just saying the set of whole numbers, it doesn't work out. It's basically, it's not just every element has an, I should say, because not every element has an inverse. It's not just that this is the only one, it's actually that every single number in this set, except for 0, does not have an inverse. That's a whole number. 1 plus negative 1 is 0, but negative 1 is not a set, or is not a number in this set. Only 0 plus 0 actually has the identity element, or has the inverse of itself. 0 is its own inverse in that case. Let's check out number 4. Develop a clock 5 arithmetic table. So we're going to go back to one of our lessons here. I'm trying to remember if it was this one. Yep. Okay, so clock arithmetic was here. So we had this clock 8 arithmetic table. You had the elements 1 through 8, and here we have a clock 5, or what we're doing here, it's kind of like this, but just with a circle with 5 marks around it instead of 8. So for the sake of clarity, I will draw a circle here and make sure it's not filled in. Let's do this off to the side. Okay, and then we could put around here, we're splitting this up into 5 equal parts. So it's basically like the vertices of a pentagon. 1, 2, let's say right about there, right about here, right about here, right about here. Okay. And so just like if this was going 1 through 12, our normal clock 12 arithmetic, 1 through 5 would look like this. Instead we have 1, 2, 3, 4, and then 5 o'clock in a sense would be the last hour of the day if you were thinking of clock 5 arithmetic. So to develop our table here, I will make a nice looking table with my line tools. You do the same. I'm going to draw in some light guidelines too. These can be the blue lines on your paper, just so we can see how it all lines up nice and straight. Oops. And I'll make some vertical light lines here, so that'd be 1, 2, 3, 4, and 5 right there. Okay. So let's just fill this in. We're doing addition. We're doing 1, 2, 3, 4, and 5, going in both directions. Okay, so what's 1 plus 1? 1 hour plus 1 hour in a sense would be 2. And then you'd have 3, 4, and 5, but then you do 1 plus 5, you're going to go all the way back around and back to 1. And so that same row holds down for this column too. 2, 3, 4, 5, and 1. And so 2 plus 2, you'd have 4 o'clock in a sense, you'd have 5 o'clock, but then 6 o'clock doesn't exist in clock 5, and so you'd go back to 1 and 2. And so just continue that pattern. The pattern's going to continue holding. You have this, you have this, and you have this. Alright, and is this under the operation of addition, is it a commutative group? We assume that the associative property holds. Explain your answer completely. I looked in the back on this one, and they actually didn't explain their answer completely, so I'm not real happy with that. Bad book writers on this one. So we need to check all 5 things. We need to check, first of all, do our CIIA thing here, does closure, is this a closed system? So you look at that, yeah, that's a closed system. Every element in the table itself is still one of the numbers you started with. So you can say closure checks and be good to go with that. Is there an identity element? Is there something you can add to each number to get you back to what you started with? And it looks like 5 would do that, because 5 is going to go one time around the clock. So 1 plus 5 gets you back to 1. 2 plus 5 gets you back to 2, and so on. So we can say that 5 is the identity element. And then checking step 3, we're checking if it's a commutative group, so we got to check 5 properties, not just 4. So this is the other I. Does every element have an inverse? Does there's something you can add to each number that gets you to 5, to get you to the identity element? So you can say 1 plus 4 is 5, 2 plus 3, 3 plus 2, and 4 plus 1, and then 5 plus itself. So each one has an inverse. Let's just write those things down. 1 plus 4 was 5, 2 plus 3 was 5, 3 plus 2 was 5, 4 plus 1 was 5, and then 5 plus 5 in clock 5 gets you back to 5. So every element has an inverse. So that checks out for us. We're good to go so far. Put little check marks by each one of those. Now we're going to check the associative property, but we don't have to check the associative property because it says that we can assume that it holds. So we are told to assume the associative property holds. I'm not sure why I underlined that, but I'll just get rid of that. So this A part, this works out for us. That checks. And then the commutative property, we could check and do each one switched around, or we can just remember, look at the main diagonal, this is our little trick, and see that a table is symmetric about the main diagonal. So everything that's over here, does it show up over there? 4 and 4, 5, 5, 5, 5, 1, 1, 1, 1, 2, 2, 2, 2, 3 and 3, 4 and 4. So it's symmetric about that main diagonal. So we can say this, symmetric about the main diagonal, which implies that it's commutative. So we are good to go there as well. Those are the 5 things we need to check. We've checked all of them. That means it is a commutative group. So I would say yes, it's a commutative group. So let's move on to number 6 and number 7. Determine the following in clock 5 arithmetic. So I'm going to refer back to my table here still, and think of it, whoops, a little too far there. Think of it that way. So 4 plus 3 plus 2. Just doing my addition from left to right as I would in base 10 arithmetic like we're used to. 4 plus 3, not going to be 7 in clock 5. It's going to be, what is 4 plus 3? In case you forgot, you can go back here. You can think of it as 4 plus 3 hours visually like that would get you to 2, or you can look at the table, say 4 plus 3 gets you 2 there in the table as well. So we would say 4 plus 3 gets you 2, and then 2 plus 2 gives you 4. So in clock 5 arithmetic, got to use that. We would say we have that. And then 2 minus 5, I think this one's probably easier to think of in terms of the actual picture here. 2, if you subtracted 5 hours from 2, it'd be the same thing as adding 5 hours to 2. So you'd go back to where you started, and you'd still be at 2. So this one, 2 minus 5, kind of weird. You would think, oh, -3, but in clock 5 arithmetic, we're saying this would be the same thing as what you started with, the same thing as 2. Let's keep going from there and consider now this mathematical system. So this is number 8. What is the binary operation, first of all? So what's up here is always the binary operation. Sometimes it's addition or subtraction or something we're more used to. This time it's the square, whatever the square means. The square is defined by what you have down here. This is what doing w squared w means. W squared w gets you t. S squared w gets you r, and so on. So is the system closed? Let's see, everything in this table. Is there anything new that didn't show up in the column or the row here? I would say no. So this is closed. And so I would say yes. There are no new elements in the table than what you started with. Something like that. You could say that in your own words. So what you started with. So it's supposed to be an N right there. Okay. Is there an identity element for the system under the given operation? So let's see if that's true. So basically we're looking for a repeated column. So this repeated somewhere. So it looks like here it repeats itself. So if you add t, it looks like to each element you should get the same thing from what you started with. You should have the same thing going on with the row. So if you add t to each row here, you get the same thing as what you started with. So I would say yes. The third row and column in the table is the same as what you started with. Meaning that t is the identity element. What you started with, okay. So I could say something like, therefore t is the identity elements. Okay, let's check out part D now. What's the inverse of the element r? So we're saying r plus what gives me t, gives me that identity element. R plus s gives me t right there. So that's going to do it for me. And I would also want to see r plus s the other way still gives me t, so I still see a t there. So I would say that s is the identity, or the inverse element of r. So that's sufficient there just to say s. And then what is t square r first, and then square w. So t square r, let's get rid of the writing there, okay, just to make this a little easier to see. T square r, first of all, t square r gives me r. And so I would write down that this is the same thing as r square w. And then what is r squared w? So r squared w is s, it looks like. So r squared w, I should have my final answer as an s right there. So this was it. Here the square is the answer itself right there. And so we'll just double check that and move on if we're ready. Okay, so it looks like we're good to go. Now we're determining whether the mathematical system is a commutative group, and we're going to try to explain our answer completely. So same thing as before, we need to check those 5 things and see if all 5 things hold. I will split this up. Yellow's fine for that. Why not? Why not? Because it's not easy to see. Okay, changed my mind. But let's work through number 9 here. So let's check out, first of all, does the associative property, I'm getting way ahead of myself. We're determining if it is a commutative group here. We need to explain our answer completely. So first checking for closure. Is everything in here an element that's here? So usually this one's pretty straightforward. We look at it and say, oh, yep, everything here is there. But this one, whoa, there, they tried to trick you. Here's D. Does D show up in the column or row? No, it doesn't. So D is not an element of the set containing A, B, and C, which is what we started with. So we could say the system is not closed. Therefore, you don't have to go any farther. It's got to have all 5 holding, so therefore this is not a commutative group. Okay, so that one was pretty easy. We got away with an easy one there if we check carefully to make sure that the system is actually closed. So let's do the same thing, start with the same thing over here. Everything that's in here, 3, 2, and 1. I don't see any other elements, so that's good to go. Close your checks. So let's check step 2. Is there an identity element? So is there something you can add to get the same thing? Looks like 2 will do that. It gets you the same column here and here, and it looks like adding 2 gets you the same row as what you started with. So 2 is the identity. So I can say that the identity element checks. So this is good, this is good. Now I'm going to check, does each element have an inverse? So we have something plus each one getting you back to 2. So 1 plus 3 it looks like gives me 2. 2 plus itself gives me 2. And 3 plus 1 gives me 2. So it looks like we are good to go with an inverse for each element. Let's say each has an inverse, and so this checks out. Right, so let's see, step 4, the associative property. Does the associative property hold in each case? So you notice in this one it does not say we can assume that the associative property holds. Therefore we've got a little bit more work to do than we normally do with one of these. So let's check and see. Let's start with this. 1 plus 2 plus 3. Does that equal 1 plus 2 plus 3 with the 2 and 3 in parentheses instead? So 1 plus 2 plus 3. This is the same thing. It looks here we gotta. I'm putting plus. Bad, Mr. Wagner. So what should I have been doing here all along? It's not plus. We're not doing addition. We're doing the binary operation is a question mark. So the question mark, what is it? How do you define the question mark? Well, the question mark is defined by what's in the table. So the question mark is 1 question mark 2 equals 1 question mark 2 equals 1. So we have 1, and then we're supposed to do question mark 3 after that. 1 question mark 3 is 2. So is that the same as 1? I don't want the parentheses to start as 1 question mark 2 question mark 3. Okay, so we need to check and see what's 2 question mark 3. 2 question mark 3 is 3. So is this the same? These two are the same. So I would say that checks. How many times do we actually have to do this? Well, we need to do it for every single possibility, so every single case. So I'm going to start off with 1 and then switch these ones around. So 1 question mark 3 and then question mark 2. What is that equal? And then I need to compare that to 1 question mark and then 3 question mark 2 in parentheses that way instead. So compare these to each other and see what you get. So with this we get 1 question mark 3 is 2, and then 2 question mark 2 is still 2. And then here we have 1 question mark 3 question mark 2. We're doing that first. 3 question mark 2 is a 3, and then 1 question mark 3 gets me a 2. So these are the same. These match up. These are good to go. So we've done with 1 out in front. Now we would have to do 2 out in front. Then we would have to do 3 out in front. So I'm going to continue that here. This one a little more tedious. You can see we haven't really done too many like this where we had to check each case, but we can see where it's kind of nice when they say just assume that the associative property holds. Here we're not doing that. So 2 question mark 1 question mark 3. Let's see what we have there. And so just just going back here a little bit to explain something, there was no other way I could write, or I could start off with 1 and then have the other 2 elements showing up than what I have here. These are the only possible combinations with a 1 out in front. So I'm going to have these 2 and then these 2, and the same sort of thing will happen with the 2 out in front. So we're going to see, is this the same as this right here? Those are some ugly question marks. Let's make that look a little better. 2 question mark, 1 question mark 3. There we go. So do these 2 equal each other? Now let's see. So 2 question mark 1. 2 question mark 1 is 1. And then 1 question mark 3. We've done that one a couple times already. So that's 2. And then 2. You have 1 question mark 3. 1 question mark 3 is 2. And 2 question mark 2 is 2. We did that one before already as well. So I'm going to continue this idea up here. So this is part 4 still continued. So let's check out now 2 question mark, 2 question mark 3 first, and then 1. See if that's the same as 2, and then 3 question mark 1 first. So what's 2 question mark 3? 2 question mark 3 is 3, and 3 question mark 1 is 2. So is that the same as what we have here? 2 question mark, do 3 question mark 1 first. 3 question mark 1 is 2. So 2 question mark 2, that's 2. These are both the same right here. And so that's checking out. That's good to go. So we'll check mark right there. Okay, and then now we just need to check for 3. If 3 was in the front, does this work out? So let's do 3 question mark first, and then 2, and then do 3 question mark 1 question mark 2. So we're going to check and see if these 2 are the same, and then we're going to check and see if these 2 would be the same. This one compared to this one. So let's see. 3 question mark 1 is 2, and 2 question mark 2 is 2. That one seems to show up a lot. So 3 question mark, then you have 1 question mark 2 is a 1. 3 question mark 1 we figured out was 2 already before. So these 2 check out. That's good. And then 3 question mark 2 is 3. And we know that's 2 from before. And then 2 question mark 1 is 1. And so we have the same thing showing up again. So does the associative property hold? Yes, it does. So we checked every single possibility, every single possible arrangement there. We saw that they all gave us the same thing. So finally you need to check that commutative property, see if that holds. To do that, check the main diagonal, see that everything's symmetric about that. So 1 and 1, 2 and 2, 3 and 3, it's symmetric. Whoa, white. That looks kind of cool. But I'll just stick with my black. So it's symmetric about the main diagonal. So I would say, you could put a C here, and we know that the commutative property checks. And so does the whole thing work out? Yes, it does. So I'm going to do that in white. It sounds cool. So therefore, it is a commutative group. So it's a commutative group. Alright. So as stated before, I'll state again, if they don't tell you the associative property holds, we would have to check each one. I don't plan to do something like this on the test to you, but we should know how to do it in case it does, in case of that minor chance that it does show up. So could that happen? Might I make you do that? Yeah, I could, but probably not going to do that. So I think I had this blank page because I thought I might need it for number 10, but I ended up squeezing it all on there. So let's work on number 11 now. Determine whether the system is a commutative group again, and yes, we can assume the associative property holds. So this one, that makes me feel better. Don't have to check. That would be extremely tedious to check all the possibilities. When you start getting higher than 3, then it's just going to get pretty not redundant, but ridiculous, I think. So glad they said that we can assume that holds. So the binary operation here is this circle now, and we need to see that it's closed first. So is it closed? I just see the @ symbol, $, ampersand, and percent sign. Do you see any different elements than those four in here? Looks like those are all the ones that are showing up. So is it closed? Just close your check. You would say, yeah, close your checks. And so this is kind of our step one here. Close your checks. And so this is my C part. That's good to go. Next, check the identity element again and see if there's an identity element. So this column, is that repeated somewhere? It looks like it's repeated right here. So it looks like the $sign is my identity element. Just check the row 2. See that works out. So here's the $, and these are all identical. So we can say the $sign is the identity. So does this check out? Sure does. So next, let's check the other I, the inverse for each element. Does each element have an inverse? So it's something you can do the circle to for each element to get you back to the $sign symbol. So A circle what gives me the $sign? Circle ampersand gives me the $sign. So A, or the @ symbol I should have said, circle ampersand gives me, or equals, the $sign. And so I need to do that with each one. $sign, circle, ampersand in a circle, and percent symbol in circle. It's supposed to equal, if this is going to hold, I need to fill in the blanks there, what gets me to the $sign. So $sign gives me $sign. Ampersand, @ symbol, gives me $sign. And percent gives me $sign. So each element here has an inverse. So the inverse checks out. That is good to go. Now let's check the CIIA. Let's check the associative property. Thank goodness we don't have to check that on this one. The associative property does hold because we can assume that it does. So we're told we can assume associative property holds. So no work to do on this one. This one we can just check that off then. And then finally commutative property. So check the main diagonal. See that it is symmetric about the main diagonal. Okay, so we got $sign, and we got percent, and at. So it looks like it's symmetric. So this final C checks out. So we got symmetric about main diagonal. So does this work out? Is it a commutative group? Yes, it is, because all 5 things hold. So we can say something like this again, therefore it's a commutative group. So we're told to explain our answer. This is a explanation. This is the explanation of our answer. So now let's do some mod arithmetic stuff. So determine the modulo class to which the number belongs for the indicated modulo system. Alright, so number 12, do that over here. Okay, so 64 mod 9, what does that equal? If you forgot how to do this, remember it's just basically, think a long division with the remainder. So 64 divided by 9, you'd have it 7. You'd have a remainder of 1. So 7 remainder of 1. What does this equal then? So 64 mod 9 equals 1, because the remainder is a 1. So the 7 part doesn't really matter how many times it goes into there with modular arithmetic. It's just a matter of what the remainder is. And so doing the same thing with number 13. 58 mod 11. If you divide 58 by 11, how many whole times does that go into there? It's 5. Subtract 55 and you're left with 3. So a remainder of 3. This is what matters for modular arithmetic, the remainder again. So this is going to be the same thing as 3. So 58 mod 11 is 3, 64 mod 9 is the same thing as 1. Alright, let's move on to numbers 14 through 18 all have the same instructions. We're finding all the replacements for the question mark less than modulus that make the statement true. There might be more than one since it says all replacements. So this is more like what we did here in the 10.3. This is things of this nature, not quite there yet. There we go. So one's like example 5 here, one's like example 6 as well. So we have these to refer back to. But let's start off here with number 14. So 7 plus 7 equals question mark mod 8. So this one I would say 7 plus 7. Normally for us that would be 18 or 14, excuse me, but 14 in mod 8 we're talking about this number here is has to be less than the modulus. The modulus is 8. So this is the same thing. If you divide 8 into 14, you'd be left with a remainder of 6. So this would be 6 mod 8. So your answer is going to be 6. And so I'll just box that part in. Our answer here is what goes in the question mark. 6 goes in the question mark. Okay, so what could go in the question mark here? Question mark minus 3 is, this is congruent to, not equal to. So I meant to do that up here as well. Okay, so this is congruent to 4 mod 5. What can go in the blank here? So it's a number that's less than the modulus. You might say at first, you would correctly be saying 7 minus 3 would be the case there, but remember this number has to be less than the 5 itself. And so from 10.3 I pulled up one similar to that. So this was similar here because this, I can't leave that as my final answer because 15 is not less than 13, but you can, since it's modulus 13, you could subtract whatever that modulus is. It's going to give you the same remainder. If you add or subtract the modulus from a certain number, it'll give you the same remainder in the end. So we'll apply that to this problem, and we could say that this is the same thing as 7 minus 5 minus 3 would be congruent to 4 mod 5. And so 7 minus 5, that's the same thing as 2 minus 3 being congruent to 4 mod 5. And so my answer, my question mark, is that part right there. It is the 2 itself. So now let's check out 16. 3 minus something congruent to 7 mod 9. So whatever goes in here has to be less than this number here. Well, I know that I could put in a number here, but I'm going to refer back to this one here in a second before I start explaining that. So remember, I can add anything, add the modulus or subtract the modulus to any number I have over here, and it would give me the same remainder. So I'm going to apply that to this problem again. So to this I can add, before I do anything, I can add a 9 to that 3, and this would be an equivalent statement. So what is 3 plus 9? That's 12, and then 12 minus what number gives me 7? I hope that's clear, that that would have to be a 5. There's no way around that one. And so since I added 9 here to this number, 3 minus 5 would be the same thing as 12 minus 5, because that 9 added, the modulus added to the number here doesn't affect the remainder. The remainder still would be 7. Alright, so let's check out number 17 now. It says 4 times 2, now we're doing multiplication, being congruent to something mod 6. So let's go back to 10.3 here again, just as a reference. So these ones more like this here. We got to check each number, this time being 0 through 5 in mod 6, and see which ones give me, with the question mark getting filled in, give me the right thing, the thing I want. So 4 times 2. 4 times 2 is 8. This one's actually a little different than this one, because these ones had the question marks on the left side. This one has a question mark on on the right side here by where the modulus is. So 8 is the same thing as something mod 6. And so there's really no way around what's here. 4 times 2 has to be 8, and 8 is congruent to what's 8 divided by 6. That would be 1 with a remainder of 2. So this question mark, the only thing that can go there is a 2. So the 2 is my answer, my final answer there. And then finally, checking 3 times something, question mark, is congruent to 2 mod 6. So what can go in the numbers here? We're going to check each number less than the modulus and see, oops, see the modulus. So we're checking, in other words, 0 through 5. We're going to see which ones of those work out here. So we've got 3 times 0, that's congruent to, that would be 0 mod 6, so that doesn't work. 3 times 1 is congruent to, not 4 lines, 3 lines, there we go, is congruent to 3 mod 6. That equals 3. 3 times 2, that would be 6, but 6 in mod 6 is 0. So this one, just to refer back to another one here, this one was like this. So 2 times 1 is 2, 2 times 2 is 4, but 4 mod 4 is 0, 2 times 3 is 6, but 6 mod 4 is 2. Just like that one we did in the notes before, we're doing the same sort of thing here. So 3 times 3 now, let me just see, that one had, yeah, that one was mod 4. So we had 4 digits to check here, we've got 6 digits to check here. And so this is going to be, this would be 9, but 9 in mod 6 would be 3. I'm starting to notice a pattern here, 0, 3, 0, 3. And just to check, let's see that those last ones hold true to that pattern. 3 times 4 would be 12, but 12 mod 6 would have no remainder. And 3 times 5 would be 15. 15 mod 6 would be the same as 3, so it had a remainder of 3. So does anything work out here? No, it doesn't. So there is no solution, you could say, something like that. The book, the back of the book has the empty set, so you could write it like this, or you could write it like this. There's no solution, empty set. You could even write something like that. So the null set, nothing works in there. Okay, so number 19, to what number is 103 congruent to in modulo 7? So I think a pretty easy one here. But 103 in mod 7, just divide by 7 to figure that out. This would be a 1. You'd have 13 left. You'd have a 1 here. Subtract 7, you'd have a remainder of 6. So what is it congruent to? The remainder is what matters. So 103 is congruent to 6 in mod 7. So this is the number that matters there. And that's why I check my answers. So I'm trying to go too fast there, I think. That should be a 3. That should not be a 1. Let's put that in black, which would make this different. This would go into here. This would go into here 4 whole times. That would change my remainder. So we'd have 4 times that would be 28. And that remainder would be 5 then instead. So 28. If you caught that mistake, good job, because I did not do that right. Now I look at that and I check the back and I'm good to go there. So 5 is what 103 is in mod 7. So this would be a remainder of 5. That's why that's the answer right there. And then number 20, a modulo 5 multiplication table, first of all, for part A. So what does that look like? If you need a refresher, you can go back to 10.3. You can notice we did a mod 3 addition table in the notes there, but now we're going to do a mod 5 addition table. So we check all the digits 0 through 4 instead of 0 through 2, since we're doing mod 5 instead of mod 3. And so we'll have a multiplication table as well. So I'm going to put an X instead of a dot. I'll put an X there, and I will make some nice straight lines. Might as well use the line tool if I got it. across here, I'm going to have 5 rows, 5 columns. So here's 0, 1, 2, 3, and 4. I can just move that up a little bit. I don't want to use the digit 5. It's just going to be the digits 0 through 4. And then going vertically, I also want some lines going this way. You can use the blue lines on your paper. If you just keep them nice and straight, you should be good to go too. I'm just doing this for clarity. And so I'll just slide all these guys in a little bit. There you go. Alright. And let's fill in our table here. Oops. With the numbers 0 through 4, the digits 0 through 4. These are the digits that are allowed in Mod 5. So 0 times 0, that's 0. This would be, 0 times 1 would still be 0. My fault. And this would be 0, 0, and 0. And you will notice in 10.3 that the addition table, we're doing addition. So that's a little different here than what we're doing. We're doing multiplication now. So we're actually multiplying these things. We're going to have 0 all the way down there as well. What's 1 times 1 in Mod 5? That's 1. 1 times 2 in Mod 5 is 2. And 3 and 4. 1 is going to be the identity element. So this would be the same thing going this way. 2 times 2 would be 4. Now it's a little trickier. Now I have to think of what the remainder is. 2 times 3 would be 6, but 6 mod 5 is 1. 2 times 4 would be 8, but 8 mod 5 is 3. And same thing is going to hold going this way, so we have a 1 and a 3. 3 times 3 would be 9. 9 mod 5 would be 4. The remainder would be 4. 3 times 4 would be 12. 12 mod 5 would be 2. So we've got a 2 here and a 2 here. And then finally we'd have 16. But 16 in mod 5 would be a 1. And so this is our multiplication table for mod 5. So part B now, is it a commutative group? So we need to check those 5 things one more time. So let's check out first, is it closed? Everything that's in here is an element of what we started with. So we can say closure checks out. And I will put a C here next to that. Put a check by that. So let's now check step 2. Is to see if there's an identity element. And 1 was that identity element. You multiply anything by 1 and you get what you start with. So identity is the number 1. And you can put a check mark there by that. Next up, step 3. We can check and see. And so we check, is there an inverse for each element? So let's check that out. And let's see what we got. So you have 0, first of all, times something has to give you 1, has to give you the identity. 1 times something has to give you 1, and so on. And so 0 times something, is there anything? 0 times anything, does it give you 1? No, because you multiply 0 by something, it always gives you 0. So there is no identity, or no inverse, excuse me, for 0. So this is a counterexample in a sense. So we can say therefore, if we check that, this does not work. We could put X through there, it doesn't work out, therefore the group is not commutative. I was getting a little worried that I was going to have to do the associative property for this one. That would be pretty nuts. But because the inverse didn't hold for each one, the inverse actually holds for every other element, because you can do 1 times 1 gives you 1, you can do 2 times 3 gives you 1 in mod 5, 3 times 2 gives you 1 in mod 5, and 4 times 4 gives you 1 in mod 5, but 0 times something, nothing here, times 0 gives you 1. And so the group, because the inverse didn't hold for each element, the group was not commutative. As a reminder to you, here in Chapter 10, there is more you can do if you want to review some more problems. All these answers are in the back. Check them as you go. All the answers were in the back for this practice test as well. But I was checking those answers as I went, and glad I did, because otherwise I would have made a mistake here on number 19. Always be checking your answers as you go through things. Let me know if you had any questions in class about what we did there. Hopefully you found that extremely helpful in preparation for your test coming up very soon. All right, have a good one, everybody.